you guys want to get started, I guess? I sent out an email, see if we can stragglers.
We'll wait a couple more minutes.
Yeah, I remember someone saying that there's like a free fire meeting right now too.
Oh yeah, there is.
So I think that's why a lot of Kristen students are not here.
That's a bummer. Yeah, this 12 p.m. time slot that people are still getting used to.
Yeah, I liked the old spot, but I had to move it because I hated the class.
Yeah, I understand.
I really didn't want to move it, but
I mean, that is something the school just shouldn't have skipped.
They're still not.
oh, next semester I want to be open. Yeah.
I can help you. I can put you your organizational efforts.
Busy at 7.
Yeah, definitely.
I don't think Julie has tried to log into Hogwarts yet.
Okay, I thought she said that she tried it.
She wasn't able to?
She wasn't.
She wasn't? Okay. I didn't see anything in her directory.
We'll wait a couple more minutes.
Yeah, I think she'll try.
Okay, as long as she's
I gave her, I told her like where the data was that she needed. So I think that she, well, I may ask you to check the permissions on it. It said add and make a directory for it in the data under directory. So when I make a name, sometimes it doesn't give everybody access.
I don't know where.
So I'm sure
Okay, yeah, let me know what they're.
I think it's a little early for me to figure that out. You know, I gotta go day by day, but now I'm not worried about where I'm going. Just go day by day. Try not to send up.
Yes, I agree.
it's like email breaking sounds like a dream, but in reality.
It's a dream when it's done, but then when it comes in, and you got 10 times as much to do.
Right, exactly.
I think it's on there because I'm not trying to send any crazy text. Okay, I think we'll get started. So, oh, we get applause before the talk. Yeah, so it's my pleasure to introduce Miguel Bernardez, who I think most of you know. I was just remembering when I first met Miguel and he came to visit, and he had been doing work with weak temperature gradient simulations, which he's making use of in this work as a master's student, and looking at tropical cyclogenesis. He does some interesting work related to that. It's actually, he'll show a plot that's from that work. But in particular, what I was remembering was that he told me he was interested in moisture precipitation relationships and why there was a particular pickup at a particular spot in moisture precipitation relationships. So moisture increases a little bit, precipitation increases a lot. And I was just remembering that because now he, I think, kind of has an answer to that question.
Yeah.
It's been a roundabout process to get there. So we kind of have been looking at vertical motion profiles, and he took part in a field campaign that he's going to show you some data from called OTREC. Yeah, but I think that's cool that on that visit he was expressing that he was interested in that, and we've actually managed to make a project that has gone in that direction. So, yeah, okay. So, pretty excited to hear his talk. Thanks everybody for being here.
Can everyone hear me okay? Not too loud? Okay. So yes, today I'm going to be talking to you about vertical motion profile shapes in the tropics and what controls them. And today's talk comes to you in 4 parts. First, I'll be talking about the vertical motion profile shape and some basics about it and basics about the tropics and what we know currently about it. Then I'm going to go over the WTG simulations that are the basis for my research contribution and a plume buoyancy model that we use to help understand the vertical motion shape. Next, I'll talk about the controls that we've uncovered through our research, and then finally I'll apply those to the OTREC field campaign data and see how well our new understandings match the observations. So the very important fact about the tropics is that temperature gradient, the horizontal temperature gradients are exceedingly weak. As you can see, this is the 600 hectopascal potential temperature averaged from 1948 until now. And as you can see, there's almost no temperature change anywhere in the tropics. It's just a sea of very similar temperatures, which contrasts quite a lot with the high gradients in the mid-latitudes. And this is mostly due to a lack of rotation, which means that any temperature anomalies very quickly gotten rid of by horizontal gravity waves. And because of this weak temperature gradient, we can basically ignore all horizontal advections of temperature. So basically, anytime we have convergence of dry static energy or convection, a balancing of latent heat, it's caused by vertical motion. And this means that in the tropics, basically, anytime there's heating, there's going to be a vertical motion to compensate, because that's the only source of compensation for the diabatic heating. Plotted here is the precipitation averaged over a 3-year span from GPCP. And as you can see, there's a very nice bounding of the ITCZ. You have rainy regions and dry regions. And then down here plotted is the vertical advection of dry static energy. As you can see, there's a very close match. So basically, and as I showed before, the horizontal gradients of temperature or dry static energy are small. So almost all of these differences are due to changes in omega when you go from horizontal place from different location to different location. So the vertical velocity is connected to the precipitation, and the precipitation is connected to the vertical velocity. They're basically a pair. And I'd like to point out 2 specific regions, the Central Pacific and the Western Pacific here. These 2 regions have very different environments, have very different looks to them. The Central Pacific is a thinner ITCZ, but they have very similar amounts of rainfall, which will be important later. So next, I'm going to talk about how we describe the vertical motion shape. Shown here are vertical structures of vertical velocity, and the way we find these is we take all the vertical motion profiles from the tropics over the oceans, put them into one giant matrix with height as one axis and time and space as the other. And then we compute these structures that explain the most variance. So essentially the ones that cause the most difference in what we see. And we find that the first and second modes explain a combined 90% plus of the variance. So you can basically you only need these 2 components to explain all vertical motion changes. That lets you decompose your vertical motion omega into an amplitude of your first mode, which is basically just how much convection you have, and then an amplitude of your second mode, which influences the top and bottom heaviness, which is the important thing I'm going for, which is what I'm going to be mainly focusing on. And so, in order to combine these 2 numbers to give us a single value that describes vertical motion shape, you take a simple ratio, you get an essential amount of top and bottom heaviness that's normalized by the amount of convection. So, going from high top heaviness ratios, you have very top heavy vertical motion, and then in the reds and blues show very bottom heavy vertical motion and have negative values. However, this metric has the problem of being poorly defined when O1 gets very small, and it also has the problem of only being defined in a sensible way if you choose positive or negative O1s, because otherwise negative divided by negative would be a positive. And so in order to fix that, you can take the arc tangent, and that lets you describe the entire set of O1s and O2s. So instead of having bottom to top heavy ascent, going from blue to red, we have bottom heavy ascent in red, or in blue, going to top heavy ascent in red, but then we can continue around and we have top heavy descent, top heavy and bottom heavy descent, and then just general descent at the 180. And so this allows us to describe the entire set of vertical velocities. And so next, we apply that to the tropics as a whole. And so here's the legend from the previous plot, and here are the two boxes that I pointed out earlier that had similar precipitation rates. And as you can see, they have very different top heaviness angles. The Central Eastern Pacific is very bottom heavy, and plotted here is the vertical velocity profile from that region. And the data for this is a 10-year climatology from Era 5 from 2007 to 2017. And so you have a Central Eastern Pacific box, a very bottom heavy, and a top heavy box, or the Western Pacific is very top heavy. But they have very similar precipitation rates. And so we want to figure out what is leading and what is driving these differences. And so the importance of top and bottom heaviness is essentially comes from the energy and the fact that there's a negative, or a minimum in the moist static energy profile. And the moist static energy is just the combined energy from temperature, height, and moisture. And it's approximately conserved for moist adiabatic motions. So when you have bottom heavy vertical motion, you have air entering the column in this layer, in this small layer, and air exiting the column in this top layer. And this is a layer of non-hypertonous. And conversely, for the top heavy column, you have this big swath of air entering the column, and this big swath of air leaving the column. And that relates to the energy, and that the average energy for the top heavy one, the average energy for the air leaving the column, is higher than for the air entering the column. So you'll have a net export of energy, or the energy in their column will decrease. And conversely, you can see the air entering the column for a bottom heavy profile is higher than the air entering, than the air energy of the air leaving the column. So bottom heavy vertical motion will have a net energy import. So this means per unit of vertical motion, top heavy vertical motion will tend to export energy, and this is described as having a positive GMS. So more convection, less energy, and less energy, the less eventual vertical motion, and you have a nice closed loop. And for bottom heavy vertical motion, you import energy per unit vertical motion, so you have a negative GMS. And these have to be compensated, these tendencies have to be compensated by the rest of the atmosphere. So, next the question is, what controls this top and bottom heaviness? And there are two main mechanisms, two ideas for what controls the vertical motion shape. The first is a dynamic mechanism, which uses a combination of the SST and the gradients of SST. So using the bottom, the lower boundary layer, or the lower boundary condition to describe the shape. And then the stability mechanism, in which the top and bottom heaviness is controlled by the large-scale temperature profile, or the large-scale temperature stratification. To go into a little more depth, the dynamic mechanism starts with, you have a layer of ocean with warm SSTs on one side and cold SSTs on another. These imprint on the boundary layer and drive a resulting wind. This creates a convergent flow in the boundary layer, which through mass continuity drives a vertical motion near the surface. When you have high SSTs, higher than average SSTs, this drives more top-heavy vertical motion. And so in the absence of high SST, when you have this convergent flow, you get bottom-heavy vertical motion. So the evidence for this, if you make a very simple model of the dynamic mechanism, you essentially have a deep top-heavy mode that's controlled by the SSTs, and then a shallow bottom-heavy mode controlled by the Laplacian of SSTs, or where SST gradients are. Then you linearly combine these two modes in the same way as the EOF modes that I showed earlier. Then you can calculate the rain from the dry static energy budget, which this is fairly static horizontally and in time. So most of the variability comes from the vertical motion. So you combine the dry static energy budget, vertical motion, and calculate the rain, and you find that it matches precipitation really well. It can even beat the climate model, so the dynamic mechanism is very good at showing the vertical motion shape. Next, to move on to the stability mechanism. First, I'm going to describe what I mean by stability, and this can be encapsulated by a very simple metric called the Instability Index. Plotted here is the saturated moist static energy, basically the maximum moist static energy you can have before condensation starts. And the Instability Index is just the energy average over the lower atmosphere minus the energy average over the upper atmosphere. So if you have a much warmer lower troposphere, this line moves to the right and you'll have a higher instability index. So your stability is less. You have more instability and vice versa. When this is cooler, you have a lower instability index and your stability is higher. So when I say we have a column with high stability, I mean it either has a smaller difference between the lower and upper tropospheric saturated moist static energy. And so looking at the observations, they've shown on the right is a plot of the instability index and the gross moist stability. So the gross moist stability, again, is how much energy is imported or exported from the column for an amount of convection. And so basically the gross moist stability predicts how much intensification you'll have. And the instability index and gross moist stability are negatively correlated. And this is data from the PREDICT and T-Park field campaigns, which studied cyclogenesis. Essentially, they flew a plane into storms that they thought might grow, and tried to measure what was leading to intensification. And these green dots intensified within 48 hours of the observations. So as you can see, they tend to cluster, the intensifying cases cluster around having low gross moist stability, as you'd expect, but they also have low instability index. And so the bottom heavy vertical motion is correlated with the low instability index and vice versa. And so you then take that idea into simulations. Shown here are two temperature anomalies that we apply to a large-scale temperature field, or an environmental temperature, in order to see what the resulting vertical motion is. And so this plot on the right is the simulated vertical motion profile from a weak temperature gradient simulation, which I'll describe in a little bit. But the basics of this are we use the thermodynamics to predict what the vertical motion should be. So when you add a stabilizing temperature anomaly, so you cool the lower atmosphere or warm the upper atmosphere, you get a very bottom-heavy vertical motion profile. And vice versa, when you have an unstable temperature anomaly, you warm the lower atmosphere, you cool the upper atmosphere, you get a very top-heavy vertical motion profile. And so those are the two mechanisms that explain vertical motion shape. And next is to try and sort out how much those two apply in WTG simulations, and trying to find out how much they are combined and how much they affect things. So next, I'm going to be talking about these WTG simulations and about a plume buoyancy model that we use to help study this. So the weak temperature gradient approximation as a parameterization for vertical motion is fairly simple. We start with a box of weather with doubly periodic domains, so essentially the left and right are connected, and then the front and back are connected, and so we have a basically infinite domain. But we only use, for our simulations, a 64 kilometer by 64 kilometer with 1 kilometer resolution. We then let that model run and develop a temperature anomaly. And that temperature anomaly is the difference between the average domain temperature and the large-scale environmental temperature that I talked about earlier. And that essentially represents the large-scale environment that isn't changing much. We use this temperature difference to calculate a vertical velocity. Basically, we take the heating equation and we assume there's not going to be an average amount there's not going to be a temperature tendency, so any temperature anomalies are going to be eaten away by vertical motion. So our omega is equal to the temperature anomaly divided by the temperature stratification and some characteristic timescale that the atmosphere relaxes over. So the higher the temperature difference, the more vertical motion. We then use that vertical motion to affect both temperature and moisture in the domain. The temperature brings the domain temperature closer to the equilibrium, and then the moisture advection acts as a moisture source for convection. And so this allows us to compute the vertical velocity as a function of the thermodynamic environment. And when I say thermodynamic environment, this is what I mean. The temperature, the SSTs at the bottom, we just use a flat SST of a single number, which is the climatological average. The horizontal wind profile, which we relax the domain average vertical motion back to this profile. We also have a profile of radiative heating and a profile of horizontal moisture advection that we calculate from the climatology. And with their powers combined, they form the WTG simulation. So let's look at the thermodynamic differences between our two domains, the top-heavy and bottom-heavy domain. The top-heavy domain is shown in red, and the bottom-heavy domain is shown in blue. Here is the temperature difference between the two. As you can see, the lower troposphere in the bottom-heavy box is cooler than that in the top-heavy box by about 2 degrees. But up at mid-levels, because of WTG, there's almost no difference. So for the moisture, the relative humidities are very similar, but the bottom-heavy box has more moisture in the lower atmosphere, and the top-heavy box has more moisture in the upper atmosphere. You've already seen the vertical velocity profiles, and finally are the horizontal moisture advection profiles. These have very different shapes, but if you take an integral over the whole layer, they move about the same amount of moisture. So the main difference between these is not a net amount of moisture transported, but more the shape of the profiles themselves that lead to that would be leading to differences. So that's the WTG across the WTG simulations and the basic thermodynamic environment from our two boxes. Next, a quick idea of the buoyancy of an entraining plume is connected to our vertical velocity profile. And by an entraining plume buoyancy, I mean we assume that a plume of air is leaving the boundary layer with some amount of energy, HP, starting off. And as it rises, it entrains air due to turbulent mixing. And as it mixes in this turbulent air, the amount of energy the plume has decreases. And so as it goes up, and it entrains until it loses all its buoyancy and then spits out the moisture into the environment. And so we have our happy little cloud made up of a bunch of entraining plumes, and these all combine to give us a vertical velocity profile. To give you a little bit more of a specific idea, plotted here are the saturated moist static energy and the moist static energy from the Utrecht campaign, and the plume buoyancies from that. The difference between each of these three profiles, the far right one, or the far left, has the smallest amount of moisture. It's the lowest 25% of moisture out of all the cases, and then the far right one is the highest 25% of moisture. As you can see, the point where the plume buoyancy crosses over the saturated moist static energy is the detrainment level. And so at this point, it will start spitting out the moisture and start moistening the environment. And as you increase the amount of moisture, this height increases. So a drier environment decreases your buoyancy faster, tilts to this line further towards your moist static energy, and detrains moisture at a lower level. And the difference between the plume buoyancy and your environmental temperature is essentially is similar to CAPE and is a measure of your buoyancy, and is related to the vertical motion profile. So, with all those tools explained, let's look and see what we have uncovered about the vertical motion shape and what controls it. Quick reminder on what we're looking at. It's the Western Pacific warm pool box and the Central Eastern Pacific bottom heavy and the top heavy box. And we find when we simulate with the weak temperature gradient, we're able to get bottom heavy and top heavy vertical motion fairly well. The bottom heavy box has less vertical motion than observations, but it's still shape-wise, they're very close. They're closer to the aerified climatology that we use as the basis than they are to each other. So we're able to simulate the vertical motion shape from just the thermodynamics. As a reminder, we haven't imposed any sort of SST gradients or convergence. It's just the thermodynamics that are leading to this. So the next question is, what part of the thermodynamic environment is leading to these differences? In order to test this, we create a simulation switcheroo in order to test the sensitivity. So we start off with our top-heavy environments and our bottom-heavy environments. And then pairwise, we just switch one of the factors. So we switch the top and bottom-heavy temperature, we run the simulation again and get a vertical motion. Then we switch the SSTs and do the same on and on through with radiation and moisture convection as well. Then we take all of the simulations with the same characteristics, so the bottom-heavy temperature, and then these two would also have the bottom-heavy temperature. We average all those together, and that gives us the average vertical motion with a constant temperature profile. Then, if you subtract these two, that gives you the sensitivity to a change in that. So, if we take the bottom-heavy box minus the top-heavy box for temperature, that would give us the sensitivity to changing the stability from more stable to less stable. So essentially, what the vertical motion looks like because the temperature has changed. And so, when we do that, this is what we come up with. This is the vertical velocity at the x-axis, pressure is the y-axis. The dotted line is stability, dash is SST, dash dot is the moisture convection, and then the pure, or the small dash line is for changing the radiation. And for stability and radiation, I've done east minus west to show the effect of having more stability, and for the radiation to have the appropriate sign on here. And so for SST and moisture convection, it is switching to a higher SST or switching to the West Pacific or top-heavy moisture convection. As you can see, the two biggest effects are due to the stability and SST, which we somewhat expected. You can also see that the SST change is very negligible in the lower atmosphere. It pretty much only increases this upper lobe in the top of the atmosphere, which is very similar to the deep mode from back in Brotherton 2009. The stability, on the other hand, has this double lobe where it increases both the lower and upper atmosphere. And so this is for the stability that's switching from the west to the east. So that's stabilizing the profile, increases vertical motion, as we expected. And this means in order to get the bottom heavy vertical motion, you need to have both a low SST and a high stability. And so next, a brief look at what the plume buoyancies show from this. And it's a little hard to read perfectly, and a lot of differences happen depending on the entrainment rate you pick. But the two highest vertical motion profiles have the highest mid-level temperature difference, or the most buoyancy in the mid-levels, and then the weakest have the least. And so that works fairly well, and that makes sense to what we expected to see. But I pointed out that both stability and SST matter, so we have to essentially reconcile our two mechanisms. We have, from observations, that SST gradients predict bottom-heavy vertical motion, and high SSTs predicts top-heavy vertical motion. And so we still have this picture from the dynamic mechanism, but we've also shown that the higher dry static stability leads to more top-heavy vertical motion, and vice versa. So this, both the stability and SST matter, and so we have to combine them. So just as a quick reminder about the instability index, and to point out one thing, we saw that the mid-level temperature, which this saturated moist static energy is a function of, basically doesn't change between our two boxes. So this is held constant. However, the SST has a large effect on the lower troposphere. So essentially, when we have lower SSTs, we should expect a lower instability index, because this temperature should decrease and pull to the right, left. And so, looking at the data, comparing the SSTs to the instability index, and this is each month from the 10-year climatology that we use for our data. The diamonds are from the East Pacific or bottom heavy box. These circles are from the West Pacific or top heavy box. And the colors represent the vertical motion angle or the top heaviness angle. And as you can see, there's a very clear correlation between both SST and instability index, as we expected, but also between instability, SST, and the top and bottom heaviness. Top heavy profiles have higher SSTs and higher instability indexes. And we see a very nice correlation between the SST and instability index with the West Pacific cases. However, there is not that tight correlation with the East Pacific or bottom heavy. So something else is controlling the stability. And this is where the dynamic mechanism comes in. So normally, because of the weak temperature gradient approximation, we have some heating, and this is balanced by vertical motion. However, because we have dynamically driven vertical motion that comes from the SST gradients, we have a compensating heating effectively. So this large-scale convergence acts as a large-scale cooling, which stabilizes the atmosphere and leads to more bottom heaviness. So these essentially combine to, or this is how our dynamic mechanism is forcing, or is being felt and through the thermodynamics. And this can be explained as a moisture quasi-equilibrium, which has been studied in the literature for a fair amount. So this diagram is the basics of it. When your cloud is in an environment that's too dry, it'll lose buoyancy really quick, entrain air into the atmosphere, and won't grow very big. As that progresses, it gets to a just right state where it's happy and isn't entraining or detraining. But when it's too moist, dry environmental air gets entrained, large-scale subsidence dries out the atmosphere, and you tend to have a decrease in moisture. In sessions 2019, they put it, moisture quasi-equilibrium is the mechanism by which the moist convective instability controls column moisture. Convection adjusts to changes in the stability. These changes modulate the import of environmental moisture, and this controls the precipitation rate. So top heaviness helps determine the environmental import and export of moisture. However, the previous research only considered the column moisture. And we think that you have to consider a more vertically resolved idea of the moisture. And to show this, here are the simulations that from earlier that showed the stability mechanism. And so here are the temperature anomalies that we added, the stable one and unstable one, and the resulting bottom heavy and top heavy vertical motion. Shown here are the relative humidities from those. And as you can see, the stable case has much higher moisture in the lower atmosphere and lower moisture in the upper atmosphere. And this has the effect on the plume temperature differences, or the buoyancy that plumes feel, of increasing in the lower atmosphere, which matches the increasing vertical velocity, and decreasing in the upper atmosphere, decreasing vertical velocity. So our plume temperature differences are help connect why our vertical motion shape is changed because of our temperature anomalies. In order to, so the next step is to find a simple way to describe that effect in the moisture, the vertically resolved moisture. And to do that, we introduce the moisture dipole coefficient, which instead of just integrating the moisture all the way up to the surface, the blue line shows the moisture, the orange line shows the saturated moisture. So normally you would integrate the moisture all the way up and divide by the integrated saturated moisture all the way up to essentially get a column relative humidity, how much moisture your column has relative to how much it could have. We cut the atmosphere in half at 600 hectopascals, which is approximately the freezing level, and take the difference between those two values. So essentially we integrate from the surface to 600 hectopascals, and then divide by the integrated saturated moisture, and we subtract the integrated moisture from 600 to the surface. And that gives us essentially a measure of a moisture dipole. When the moisture dipole is high, we have more moisture in the lower atmosphere, and when the moisture dipole coefficient is low, we have more moisture in the upper atmosphere. And so that's our basic understanding of the mechanisms from the WTG profiles. Stability and SST are the main controls of shape, and they act through a vertically resolved moisture quasi-equilibrium, which I'll explain in more detail in a little. But let's check whether these match what we've observed. And these observations come from the OTREC field campaign, which was specifically designed to measure vertical velocity in the Central Eastern Pacific and Caribbean. And the field campaign consisted of 22 flights, dropping over 600 dropsons, each about a degree apart, over 2 months. And we flew in these two patterns, one off of the Costa Rican coast, and then one across Panama in the Bight of Panama and in the Western Caribbean. And then we used a technique called 3D bar to construct a quarter by quarter degree grid of the thermodynamics and wind profiles. And we calculate the vertical motion by essentially anything coming in or going out using mass continuity. You then construct the vertical velocity shapes. So taking each one of these quarter degree by quarter degree points from each of our 22 flights, I calculated the moisture dipole coefficient for each of them, and then the instability index for each of them, and these are shown here as the tiny dots. And you can see there's a very clear correlation. Higher instability index has a lower moisture dipole coefficient, which means has more moisture in the upper atmosphere, and lower instability indexes have a higher moisture dipole coefficient, so they have more moisture in the lower atmosphere. So that follows from what we expected, but the next step is to see if this also is seen in the vertical motion shape. Shown here are 4 vertical motion profiles, each comprised of a quarter of the points of MDCs for the highest quarter, the highest 1/4 of points according to the column moisture. So we looked at only the highest column moistures and then separated them by the MDC. The tall moisture cases had very top-heavy vertical motion, which means that the highest instability indexes, the lowest MDCs, had top-heavy vertical motion, and the shortest moistures, the ones with the lowest instability indexes, were the most bottom-heavy, which is what we expected. So we have high MDC, short moistures are bottom-heavy, and low MDC, or tall moisture, are very top-heavy, which is great. That's exactly what we wanted to see. So how is this explained by a vertically resolved moisture quasi-equilibrium? Shown here again is the instability index, and you can think about this as the total amount of moisture before a plume is saturated, and basically is how much moisture the atmosphere needs. So when a layer with a warmer temperature will need more moisture, and a layer with a lower temperature will need less moisture. And so when you have too low moisture, your column will detrain earlier and start moistening earlier. And that means when you have a more stable environment, you need less moisture detrained to get vertical velocity. So essentially it changes the critical amount of moisture needed to switch between the too dry and too moist state. So at the lower level, when it's stabilized, we need less moisture, and so we can get bottom heavy vertical velocity more easily. As it increases, so as moisture is detrained, we then get excess moisture, and suddenly the plume can now rise considerably higher and start moistening at a different level as it gets through. But that level, because of the excess buoyancy, has increased vertical velocity and has a resulting subsidence with dries. So at each level you have to consider that process of moistening and drying at each level, and we've split it into two. So bottom heavy vertical motion happens in a more stable environment because the critical moisture is being changed, and you essentially have a bottom heavy moisture that comes along due to the instability index changes. And that is the story. The vertical velocity variability is controlled primarily by SSTs and stability. The dynamic mechanism affects the stability, and thus the SST and stability are connected through the thermodynamics. The buoyancy of an entraining plume connects the vertical motion and thermodynamics, and allows us to see the vertically resolved profile and understand moisture quasi-equilibrium, which helps explain the vertical motion shape. And thank you. Are there any questions? I think students first. Yeah, Juliet.
First of all, great talk. This is really cool. I'm curious what the parameters were with your interactive and enclosed radiation. I noticed that the interactive radiation profile did very well. It looked like it was very similar to the data.
Mm-hmm. Yeah, so basically the difference between the interactive and the imposed radiation cases is our interactive radiation cases, we let the model compute radiation on each time step, and it evolves interactively along with the vertical motion. The imposed radiation case, we use our model to essentially simulate a version of the atmosphere, so we impose a vertical motion as opposed to letting the model simulate it. And that essentially gives us all the parameters of the model in a environment that reflects reality. And so we take that radiation case and impose it into this. And so the differences between the interactive and the imposed is essentially how tied the radiation is to the vertical velocity shape and to the rest of the environment. And so it does perform well and somewhat better depending on the circumstance. But the problem is it can lead to, or it increases the likelihood you're going to fall into a dry equilibrium, which is what this line represents here. And in a dry equilibrium, that's a runaway case where the moisture starts or leaving the column, and then there's nothing to recover it, and so it just becomes non-physical fairly quickly. And so we would like to use the interactive radiation case because that allows you to understand in a more connected way. However, we have to avoid these dry equilibriums because they're not helpful for understanding anything.
And we have some ideas for how to do that we
Yes.
just haven't had a chance to implement.
Okay, yeah, I misread the line. Sorry, I just have a follow-up question. So do you have perhaps a hypothesis for how we could, or how this interactive radiation influences the environment and that kind of changing the environment, and then also
effect that happens, radiation should have two sort of different effects. One is a direct radiative heating causing vertical motion changes, and the other is altering the essentially equilibrium between vertical motion and the energy vertical motion is affecting and the radiation. So top-heavy cases have less radiational cooling. The clouds are higher, have a lower temperature, and therefore radiate less. So there's less cooling, and that compensates for the vertical velocity changes. What that should in effect do is it changes the amount of moisture that is needed to, or the moisture that's advecting has a different equilibrium point if the radiation is allowed to change. And so the climatological average that we find would be affected. And so it's sort of chicken or the egg, where it's, the radiation leads to a case where bottom heaviness is easier and bottom heaviness has a lower radiation. I don't know if that answered your question.
No, but I understand. Yeah, thanks.
Yeah. Any other questions? Yeah.
Yeah, so you did a sensitivity test to see what components, were affecting the vertical profile. I have two questions. The first one is, did you try like multi-component analysis, or you did one of each?
No, we haven't. And that's partly to keep things simple and like limit the amount that we can do. But that's actually pretty much the entire reason. Yeah. What was the?
And then the second part is, so you end up with the relative changes. Did you like add those all together and compare them to the full case, and then like get a residual?
No. Very simply, we just added all of the cases with the same profile. So the basic case was included, and so we didn't really try looking at what differences from equilibrium was caused, because essentially east minus the equilibrium and west minus the equilibrium, then when you subtract them, the equilibriums drop away, you have east minus west anyway. So in showing what, or in trying to look at the direct switching from east to west, it made more sense to do it this way.
Okay. Yeah, I guess.
It's nonlinear.
Okay. So you would expect the residual.
You would expect the residual because it's nonlinear.
Okay.
Great.
Is the primary mechanism for detraining moisture through precipitation or just mixing into cloud?
Sorry, what was the question?
Is the main mechanism for detrainment precipitation or just mixing within the cloud? I'm not sure. I believe, from my understanding, it's mostly entraining outward, but so entraining within the cloud, but sorry, let's see.
So it's mixing.
Yeah, mixing with environmental air, sort of at the cloud edge, I believe, but I'm not sure at the.
It seems that either one can give that result.
Yeah, I think it also might be a sort of two sides of an accounting book where they're somewhat equivalent. I think if you are to look at the role of precipitation, you then have to consider where the moisture is also evaporating as it falls for things like stratiform rain. And so I think it's easier to think about it as a mixing with the environment, and then sort of allow the different effects to, let me try and think of a better way to describe this. Essentially, it's more simple to model it as just mixing with environmental air, but I'm not sure in the actual environment how they're.
I think Berg is just trying to say that precipitation can affect the environmental moisture too through re-evaporation.
Yeah.
So, but in our picture, we're thinking of detrainment and mixing with the environment rather than that process. We haven't thought about how the precipitation and re-evaporation would affect things.
One of the reasons I bring this up is this this whole mechanism you're looking at is very similar to Perry Manuel's Carnot cycle for a tropical cyclone. And essentially the shallow convection is leg 4 of that model, which is radiation and cooling of the atmosphere brings theta, potential temperatures colder and colder sinking.
Yeah.
Until you get to a point, but to get that lowest 300 millibars, you would need what he describes as evaporation and precipitation to complete the cycle to the ground. And then this whole thing is driven by radiation to space, of moist down, dry, more or less. And it describes a radiative convective equilibrium. But in order for the radiative convective equilibrium to be explained, you have to have this low layer of moisture.
Yeah.
And it essentially raises the saturation point in metric of pressure. Saturation point is where you need saturation on the way up. It lowers the saturation point by moistening that lower layer. It's the only way you get air to the surface. You notice that the theta E minimum is always around 700 millibars. It's that lowest 300 millibars that needs this shallow convection to complete the cycle. And then, if you look at what he's saying, the whole cycle is driven by this net energy gain through the Carnot cycle and cooling to space at the high levels of deep convection.
Yeah. I believe the current understanding now is that lower 300 millibars at that lowest level behaves through boundary layer quasi-equilibrium, where the air that's being mixed in and coming out are the compensation. So.
I think that's conventional wisdom, but I think you're actually explaining it here.
Yeah, this should definitely tie. That also, I think, comes into some ideas of where that boundary layer top is and how it changes and evolves, and how that fits into this whole thing. Something definitely want to better have a good description of in the future. Yeah, thank you. Any other questions? Yeah, Anna.
So I have two questions, and I don't know if they're super related to each other. So one of them is like, I kind of want to see if we can get to kind of like a layperson-friendly definition of what moisture quasi-equilibrium is, because it looks like it's like some kind of like two-way street interaction whereby the convection is affected by the buoyancy, but the entrainment by the convection is injecting air from the environment, which can kill the updraft, but then the updraft, as it gets killed out, then start moistening the environment. So at some point you kind of reach some kind of equilibrium where both the moisture and the convection reach some kind of like happy point in which like they kind of get to some quasi-steady state. Is that like a fair way to describe the equilibrium?
Yeah, I think so. Just to sort of references, as plumes rise, they have a amount of, or the way I think about it is plumes, as they leave the boundary layer, have an amount of moisture, and that amount of moisture is either going to go to moistening the environment or creating further vertical motion, and it's a trade-off depending on what the environment is like, and sort of the plumes that are depositing their moisture into the environment are making the way for the next plumes that are going to rise even further. Yeah, and then that occurs at multiple levels in a somewhat continuous way.
I think this diagram is Dave Raymond's attempt at a
Yeah.
Yeah,
It's tricky though, then they don't describe it in their talks really in a very
okay.
way.
Yeah.
So.
Yeah, I just kind of like, one of the things is like, I think this whole idea is super interesting and relevant to what we see, but I often find it like that, like when I read it, like I don't really know what they're saying when they speak about moisture quasi-equilibrium, like from this talk, I think it's clear the idea that's coming across, and I think it's important because it is relevant to the observed relationship that we see between water vapor, convection, and all these other parameters. So I just wanted to like see, you know, what the definition is. So following up on that question, I'm kind of like getting stuck on something that I think matters, but like, but I just want to poke your brain at. So when you talked about the SST gradient, you mentioned that there's like adiabatic cooling on that. So like it's partly because it's in the boundary layer, but also because it's not really tied to convection. I'm kind of curious I'm trying to like think about this in terms of the thermodynamic equation. So there has to be some kind of like temperature tendency associated with the outward motion and adiabatic cooling. I'm assuming that has to be compensated somehow by either convective heating and then gravity waves kind of like offsetting that. So like I'm kind of like I'm trying to like think about this, like how that reaches a steady state in which like you don't see that there's no marked dT. If they were like, is it like cooling on the long term that is kind of compensated by these transient impulses of heating by convection, and then like subsidized by gravity waves that like are kind of like going, kind of like firing off with the convection? Is that like a fair way to think about it?
I think so. I think that gets to one thing I've sort of had struggled with myself, which is differentiating between a climatological viewpoint and more of a steady state idea, and then a more continuous time-dependent idea. And the way I've been thinking about this temperature tendency in a climatological viewpoint is the SST wants to set a profile temperature at a certain point that is warmer than what is actually happening. And so it's just averaging over a bunch of times. This is sometimes there and sometimes not. And so you have just an effective cooling over climatology. How it affects on a daily basis, I think it should be sort of that process where you have cooling, and so you have vertical motion and easier release of latent heat, and then gravity waves would spread out like you were saying. But I think my understanding of that daily variability is not quite good enough to give a super conclusive answer.
Okay.
I'm
But I
not
think
sure
that's a
it's
good
an
way to-
adiabatic cooling in the sense that you use the term adiabatic cooling,
So
because it is balanced.
yeah, so it has to be balanced by something, right?
It has to be balanced. I mean, I
Yeah.
don't think it's balanced by horizontal temperature gradients, so I think it's balanced by the Q there, the condensational heating.
Yeah, so you do get some, yeah, so this is what I've been wondering, if there's some, so like, if there were no heating, you would actually like have a cooling trend, but you have a heating from like late heat release and then like subsequent spreading out of that energy in the form of gravity waves, that kind of like causes there to be no net temperature tendency
Right.
locally. Okay, so this is like, this is something that I kind of like been pondering about, because it's not just related to like this Lindstedt mechanism, but also like this, you know, like I think for like decades now, people have been kind of like going back and forth about the role of like boundary layer friction in tropical heat convection, and I wonder if this is kind of like the way that you have to attack the problem, and how this could be all thought about in like what you just framework.
Yeah, I think so. I think this is definitely an important step for combining those ideas, and sort of it feels like there have been a lot of halfway there solutions that seem really good up until a point, and then sort of combining and thinking about it as a holistic sort of thing is going to be necessary.
Yeah, there's sort of these two-way relationship that you can have between those two terms, right?
Okay.
So you can have the Q forcing the W, or you can have the W forcing the Q.
Yeah, I'm not sure if, yeah, that's answering your question.
So it's so like last question, I'll leave you guys alone. So is the depth of the vertical motion that you get as a result of the SST gradient defined by how high the convection that's associated with that's balancing the cooling gets? Like how high is the vertical motion that you get from like this SST convergence mechanism?
Based, I think it's sort of dependent I think,
Well, in the dynamic
I'm not sure.
mechanism, it's dependent on the SST relative to the SST elsewhere.
yeah, I think it's, let me go back to,
So it's kind of,
so this is the, I think it's a process where these temperatures are constantly trying to be relaxed by WTG, but there's the constant SST heat source leading to this temperature anomaly, but that weakens as you get up in the atmosphere. And so it sort of matters how big this SST gradient is as to how big this slope is. So essentially how far away from the heat source of the SST you are and how strong that SST source is.
Okay.
so the temperature at 600 there shifts to the right or the left depending on what's going on in the rest of the tropics.
Okay, yeah.
And so the idea is that it's some kind of crude measure of what's going on near the surface minus what's going on at 600.
Yeah, so you have a local surface effect, and then basically the entire tropics helps determine the mid-level. Or the entire tropics determines the whole column, but the local features are felt much more in the lower atmosphere than the upper.
Yeah, okay, that's fine. Yeah, just been wondering, like, where, like, how deep does the surface signature, how deep can it penetrate before, like, the rest of the tropics, the WTG that's set up by everywhere else takes over as the main determinant of what causes, the
Right.
stability in the region.
Yeah.
So the argument is that depends on the local SST versus
Yeah,
the
right,
tropics
yeah.
side SST.
Yeah.
Okay.
All right, we're just out of time here, so let's give Miguel a hand.